Hi everybody, let's talk about section 7.5, which is proportions in triangles. What we're going to learn about today is two other theorems we can use, technically three, that we can use to find proportions or find missing lengths in similar triangles, but they're not necessarily just for use with right triangles, like the stuff we did in 7.4. So these can be used with any set of similar triangles. And we've got these three theorems here, and we're going to write them first in symbolic notation. So if this doesn't make sense, we'll talk about it and make sure that you understand. The first one is the side splitter theorem. The side splitter theorem tells us this. If I have triangles in this configuration that I'm about to show you, where I have a triangle, and then I have a line somewhere inside of the triangle that is parallel to another line, another side of the triangle. That's what the side splitter theorem is about. What I've done is I've split the sides into two pieces. So what the side splitter theorem tells me is if maybe this is triangle A, B, C, and I'm going to put M and N as the end points of that new little line that I've drawn in there. The side splitter theorem tells me that when I split the side with a line that's parallel to one of the sides of the triangle, I create sections of this first line which are proportional. So I could say that B over M, not B over M, sorry, the line BM, the segment BM, over the short one underneath it, segment MA, that is equivalent to the other one, BN, over its short line underneath it, NC. And also, these are both equivalent to the bases that are parallel to one another, MN over AC. So now we've created basically two similar triangles, the small one that's inside and the other one that is outside. Another thing we can do here is we can compare the other pieces here. So we can say, well, I could take this small piece BM over the entire side BA. I can say BM over the entire side BA. That's equal to the small side BN over the entire side BC. We're totally allowed to do that as well. We can say, well, this piece is in the same proportion with BC as BM is with BA. So we can make lots of different proportions with that information. The next one is a similar idea. It's called the triangle midsegment theorem. This one is going to tell us that if we have triangles that look pretty similar to the ones beforehand, if I have a triangle, and I have the mid-segment of this triangle. So remember, mid-segment is when I find the midpoint of one side and the midpoint of the other side, and I connect them together. Wow, that is not looking very midpoint-ish to me. Let's try that again. Should be something like that. All right, and this midpoint should be right there. So if I have this construct, then I know a few things. And I'll label this again, triangle A, B, C, and M, N. I know that the new line, MN, is parallel to AC, because that's what I know about mid-segments. And I know that MN, the segment that I just drew, is equal to half of AC, half the base. Just the same way that MB is equal to half of BA, and MN is equal to half of BC, MN is equal to half of AC. And then finally we have the triangle angle bisector theorem, which is a little bit different. This one tells us that if we have a triangle and we bisect an angle, so I'll say this is, again, triangle ABC, and I'm going to bisect angle O. So remember, bisect means that I'm splitting this angle into two congruent pieces. I'm not necessarily splitting the bottom into two congruent pieces. And maybe we'll say that meets at point O. Not point O, sorry. Let's use point D there, just so that I can keep this the same as what I'm teaching other classes. So there's point D. So the triangle angle bisector theorem says this. When I draw the angle bisector, I'm splitting the left side proportionally with the side lengths of the triangle that I have already. So I can say that side length AB over side length AD. So the proportion from the side I already had and the piece that I've created by putting in an angle bisector, that's equal to the other side I already had, BC, over the part that I've split the bottom by creating the angle bisector, CD. We'll see how to use these theorems today. It's going to become abundantly clear as we go that this is pretty simple stuff. I just want you to understand that you can use this with any triangle, not just right triangles, whereas you can use the stuff from 7-4 just with right triangles. So here's an example. In triangle JLN, if LN is 9.6, there's that whole thing is 9.6, what are LM and MN? Well, what we can do here is we can say, I know that LK is 3 and KJ is 5, and I can use those ideas and the side splitter theorem. I know I can use the side splitter theorem because KM and JN are parallel to one another. And I can use the side splitter theorem in a few different ways. If I wanted to find LM, I'll make that X. One thing that I could do is I could compare this side, which is 3, to the entire length of the left side, which is 8, since I know the entire length of the left or the right side, which is 9.6. So I could say 3 over 8 equals X, the piece I don't know, over the entire right side, 9.6. And when I do that and cross multiply, I get 8X equals 28.8. And I can divide both sides by 8. And I get X equals 3.6, roughly. So this piece is 3.6. Which means that MN, since the entire side is 9.6, is going to be 9.6 minus 3.6. So MN is 6 units. The question, are the sides divided proportionally, is also yes, because based on the side splitter theorem, when we have these parallel lines, the sides must be divided proportionally. So yes, because of the side splitter theorem. Right. Then down here we have BD, segment BD bisects sides AC and CE, and we can see that because we have congruent pieces on the left and on the right. Is AE parallel to BD? Well, we just talked about that, right? We know that if we have a mid-segment, which means the line is divided into the midpoint on the left and the midpoint on the right and connected together, then that mid-segment is definitely parallel to the other side of our triangle. So we can say yes because of the triangle mid-segment theorem. Because of the triangle mid-segment theorem. All right, let's keep going. This is an interesting case for the side splitter theorem because here I have a triangle that's sides are split into 3 pieces each. Now the cool thing about the side splitter theorem is we don't necessarily need to just compare one short piece to the entire side. We can compare one short piece to another short piece. And over here, the short piece on the right can be compared to the other short piece in the middle. So we can kind of pick and choose the pieces that we want to compare. In this case, it says, what is the value of X? I can do this a lot of different ways. I see an X value here and an X value here. So the way that I'll do it today is I'll just choose another piece of this side and another piece of the right side to compare to. So I can choose X plus 2, the bottom segment, over 4, the middle segment, is equal to X, the bottom right segment, over 3, the middle right segment. So I have bottom over middle on the left, bottom over middle on the right. Then I cross multiply, so I get 4x equals 3 times x plus 2. I have to remember to use the distributive property to distribute that 3. So 4x equals 3x plus 6. And then I'll subtract 3x from each side and get x equals 6. And that'll be the value of x. And of course, I could do that a few other ways. I could have lots of different proportions that would work there. I could do x plus 2 over 12 equals x over 9. That would be left bottom over top segment, right bottom over top segment. I could do x plus 2 over 16 equals x over 12. I could even take the entire thing. I could say x plus 2 over x plus, 16 plus 2, 18 equals x over x plus 12, and that would work as well. Then it says, what are the values of y and z? Again, I need to use the proportionality. I know the length of this side. Now that I know that x is 6, I can put a 6 in here and say that that bottom left piece is 8. And when I do that, I find that the entire left side is 8 plus 4 plus 12, or 24. Okay? So one of many ways that I can do this to find y is I can say, all right, I know that this piece 12 over the entire thing 24 is going to be equal to this piece y over the entire base 30, right? I'm using the proportionality with the side splitter theorem. So I can say that 12 over 24 is equal to y over 30. And I know 12 over 24 is a half, so I just, even without cross multiplying, I know that y is equal to half of 30, so y is equal to 15. But you would know that if you cross multiplied as well. And then for z, I could do a similar thing. I could do this z, which is the sort of middle line in here, and then the left segment, that 12 plus 4 is 16. And then I could use 24 as well as the left and 30 as the right, or bottom. Or I could go with z and 16 and 15 and 12 for that small triangle. So I'll do that to change it up. I'll say 12 over 15, left side over bottom side, equals 16. I got that from doing 12 plus 4 here for QS over z, that middle base. And I can cross multiply to find the answer for this one. So 12z equals 16 times 15, which is 240. Divide both sides by 12. And I get z equals 20. So I found that y is 15, z equals 20. And then I also found x in that example. Finally, I am using the angle bisector theorem. So the angle bisector theorem, which happens when I bisect one of the angles in my triangle. In this case, in this triangle, NL bisects angle KLM. It says compare the ratios KN over NM and KL over ML. And we want to find out if triangle LKN, let me outline that one, is similar to triangle LMN. This triangle right here. Are these similar or not? And we can do that by comparing the ratios. So let's first find the ratio of Kn over Mn. So Kn is 10.5 over Mn, which is 7.5. 10.5 over 7.5 is going to be 1.4. And then we will compare the ratios of KL over ML. So KL is 14, ML is 10. Those are also going to be equal to 1.4. But remember that just having two sides in proportion with one another can't be all we need to show that triangles are similar, because our side theorem is side, side, side similarity, we need to check that the third side is also a 1.4 ratio. However, the third side of each of those triangles is the side LN. The side LN in the purple triangle and the side LN in the green triangle. So if we do the ratio of LN in the purple triangle, we don't know the value, but we can call it LN, over LN in the green triangle, those are the same amount. So side length LN divided by itself, the ratio of sides LN is just 1. That's not 1.4. Since we don't have 3 equal side ratios, then these are not similar. So the triangles are not similar. Just because the triangles are not similar, it doesn't mean that the triangle angle bisector theorem doesn't work. Because these two pieces illustrated our triangle angle bisector theorem. We're not able to use the angle bisector theorem to find all the sides, but we can use them to find the relationship between the left, but the leg and the piece of the end, as well as the other leg and the piece of the end. Those will have the same ratio, even though the triangles are not similar. So we can use that idea to find the values of x, gh, and jk here. We have an angle bisector. So the ratio of the leg over the piece of the end is equal to the other leg over the piece of the end. So 3x plus 3 over 3x minus 7 is equal to 18, the other leg, over 12, the other piece of the end. And then, of course, we have to cross multiply. So that's going to be 12 times 3x plus 3 equals 18 times 3x minus 7. And, of course, we're solving this equation, so we're distributing. We've got 36x plus 36 equals 54x minus 126. Subtract 36x from each side, and we get 36 equals 18x minus 126. Add 126 to both sides, and I get 162 equals 18x. Divide by 18, and I get 9 equals x. So I know my value of x, which is 9. And of course, I can just plug it in to get GH and GK. So for GH, 3 times 9 is 27. 27 plus 3 is 30. For GK, 3 times 9 is 27. 27 minus 7 is 20. And those will be the values of GH and GK. So we can work our way around similar triangles in many different ways. We just have to note that for these scenarios, we don't have to have right triangles. But for altitude on hypotenuse, we need right triangles. The main thing that I see that people do in terms of making mistakes here is that they start applying the right triangle theorems to a question that might look like this one. But this is not an altitude, and we cannot treat it as such because it doesn't make a right angle with the opposite side, and there's no right angle up here. We can use the angle bisector theorems. The ones up above, we can use the side splitter theorems. We just can't show the altitude on hypotenuse theorems for these. All right, so good luck with your work today. Let me know if you've got any questions whatsoever, and have a wonderful day.